Hello everyone, welcome to 369 Chemistry, and in this video we are going to study about your SN2 reaction. Okay, so this is your nucleophilic substitution by molecular, and last time we did about SN1 reaction. We also solved many questions regarding that. So in this video also we are going to solve questions regarding your SN2 reactions also. Okay, so the first thing you should know that this reaction is your concerted step reaction. Okay, concerted step means here, like in case of your SN1 reaction, we have seen that it takes place in two-step process. One is the very slow process, that is your breaking of your alkyl halide bond, or you can say your breaking of the substrate. And the second step is your addition of the nucleophile. But in this case here, the breaking of the bond and the attack of the nucleophile takes place in one-step process. Okay, so the transition state of an SN1 reaction involves both the substrate and the incoming nucleophile together. The latter attacks the carbon side of the substrate from a position opposite to that of the living nucleophile. So suppose if this is the nucleophile, okay, and you have this is your substrate, okay, then what will happen, this nucleophile will not attack from the place where the substrate is, the living group is going on, but it will attack in the opposite direction. So here the nucleophile will come and attack to and can get itself attached to the the molecule, and then you are going to get your product, and your living groups separate. So this happens in just one step, and hence it is called your one step reaction. Okay, so suppose if you have, see this, so if this is the substrate, okay, and this nucleophile is getting added to it, so what will happen to it, here this one will leave and this nucleophile will go and attach in the opposite direction in this form. Okay, here now this one will give you, nucleophile will attack in the opposite direction. Suppose this is here CH3, and the living group, that is the nucleophile. Okay, so here this process actually involves one step reaction though, so the energy profile will be like this. Okay, so this is your substrate plus nucleophile. Okay, this is the reactants. Okay, then energy rises. Okay, energy rises when it forms the transition state, that is the transition contains of 5 bonds, partially broken bonds. These are your partially broken bonds. Okay, so this is the substrate which is the highest state, and when the product forms, then again the energy is lowered. Okay, so this is the energy profile. Here, this is the product, right? So since, what we can say, the this is important to write, please note it down. Since the substrate and the nucleophile file in the single step, in the single step, okay, they involve only the single step of an SN2 reaction, its rate will depend only on their concentrations. Okay, it will not it will not depend on how much easier the substrate will go out and this and that, nothing like that. Okay, here there is no slow step. Okay, rate determining step is not there, so breaking of the bonds, those things which we discuss about in your SN1 reaction will not follow out here. Here it will depend solely on its concentration. That means concentration of your reactants, and this the concentration of this, actually the intermediate step will determine the rate of SN2 reaction. If this step is easily available or easily reached, then it will easily go for your SN2 reaction. So from this study it was found that rate of SN2 depends on your substrate and the nucleophile together. Okay, so here you can say it follows second order kinetics. Second order kinetics, because here in the rate it depends both on substrate and nucleophile both. And if the reaction is carried out in a chiral carbon, then what happens? Then the product which is obtained is always the inversion of the configuration is seen. Example, for example, see this CH3, CH3, this is hydrogen, this is bromine. Okay, this is your R 2 bromooctane. Okay, so here if the Br goes out, then what will it form? It will form like this OH will attack. Suppose if you have water, okay, basic attack, that means OH minus ion attack. Okay, basic attack. That times what happens? This OH will go in the opposite direction and attack the carbon atom. CH2 whole 5 CH3. So here the inversion of configuration usually takes place, whereas the retention of the configuration is not found. Whereas in SN1 it is little bit at least found, okay, in the mixture of the products, but here there is no mixture of the product. Usually the SN inversion of configuration only takes place. Now we will go to the factors influencing your SN1 reaction rate. See, in the factors influencing your SN2 reaction rate. In SN1 reaction, the rate totally depended on the stability of the carbocation intermediate. So the more stable the carbocation intermediate is, then SN1 used to follow, and whatever it took to stabilize the carbocation, we focused on those factors. Here also there is a stability of the carbocation intermediate, but it is a short-lived thing. Here the rate depends on both the thing, that is your substrate and also your nucleophile. Okay, so let's see the factors affecting your SN2 reaction rate. The first one is the effect of substrate structure on rate. The effect of substrate structure on rate means what? It means that suppose if you have a molecule like this, okay, this one, okay, or you have a molecule like here you have, okay, so which one will go for SN1 reaction easier? Substrate structure on rate, the what depends on structure. So see here, this is electron withdrawing group. Here, this one is your electron giving group. So if it is in an electron withdrawing group, that means it is taking up the electrons of the carbon, making it electron deficient, and this one also take going out easily. So if you have something group which is electron withdrawing in nature, that means it is it is increasing the electron deficiency of this carbon. Then what happens? The nucleophile which is electron rich, it can come and easily give electrons to the carbon, so reaction is easily done. Whereas in case of your electron giving group, if it is an electron giving in nature, if it gives the electron, that time what happens? This one is already getting electron. Okay, so nucleophilic attack become very much difficult from the other side. Okay, here also one thing, it depends. If bulkier groups are there on these kind of groups this side, then it will go for SN1. It will not go for SN2. If bulkier group is not there, then nucleophile can come and attack in the opposite direction easier. So that's why we say effect of the substrate structure on rate. That means it depends not only on the groups which is there. In SN1 also it depended on the groups. Okay, electron withdrawing group make it very good susceptible for SN1 reaction also. The same thing. But here even the structure is also important. There structure was not important, but here structure is important. Why? Because in this one, if bulkier groups is there, SN2 is not possible. Why? Because it is one step process. Here the nucleophile cannot go and attack from the backside very easily. So those which will have not bulkier groups will go for more SN2 reactions. So steric factor is very important. Okay, so if steric hindrance is more, it will not go for SN2 reaction. If steric hindrance is less, then only it goes for SN2 reactions. So you write the decreasing order of your SN2 reaction. Please note it down. It is important. Okay, even if I have not given you the definition of it, I have explained you, so better write it down. That is, see, this one, there is less steric hindrance. Okay, so it is going to go for SN2 easily. Primary. Okay, so that is your primary more than secondary more than tertiary. So it is opposite of your SN1 reaction. Okay, so right, chain increases, it is less prone to your SN2 reactions. Even if you go for C branching, if branching is also there, then also it is less. So basically it is primary more than secondary more than tertiary. Okay, CH3 O3 CH2 G. Okay, so this way your decreases. Okay, so this one is best for SN1, sorry, SN2, and this one is not so good, not so good for SN2 reactions. Remember that. So again, there is exception, like you see vinyl, vinyl and aryl. Okay, these are very less going for SN2 reaction. Why? Because see, they are always more stable. No, their carbocation is more stable. So these are will go for more SN1, not SN2 reaction. So they are very much less reactive towards your SN2 reactions. Benzyl and allyl system goes easily for SN2 reaction. Okay, see why it is. BH2. So this is your vinyl. Okay, they are not prone to your SN2 reaction. This is not prone. Okay, and here aryl. Aryl means, see, you have phenyl ring, and suppose you have another phenyl ring, and CH, and suppose X. So these kind of molecule will not go for your SN2 reaction. Whereas benzyl means you have, see here, CH2 plus. Okay, this is called your benzyl system. So benzyl system, see here, though it has it is this positive sign is very much easily it is due to resonance, it is stabilized. Therefore it will go for your SN2 reaction very easily. Why? Because see, maybe it is resonance stabilized, but still you can say this is benzyl cation, but is it not that this carbon has two hydrogen? It looks like primary, and plus this is stabilized. The system is very much stabilized due to resonance. So easily this SN2 can go through backside. Here there is no more big bulkier groups. Steric hindrance is not there. Okay, it is stabilized due to resonance, and transition state can be easily attained. Even see this one, CH double bond CH. Then you have CH2 plus. This is your allied system. Allied system also, see, there is no hardly any kind of you have hardly bulkier groups is there. Okay, so allied system, they will also go for SN2 easily because bulkier system is not there. Okay, and here also it is stabilized due to resonance hyperconjugation effect, and they also react faster than your ethyl system, remember. Okay, so now we will see different examples, such as you have presence of alpha and beta halogens on the substrate. Okay, your SN2 reaction rate. Example, CH3Cl, then you have CH2Cl2. If you have CHCl3, and then you have CCl4. Okay, so SN2 reaction rate decreases in this order. That means as you who add more alpha and beta halogens, then there is a decrease. One halogen group, this is last time we understood that there is, if one electronegative atom is there, that time the reaction rate increases. But what happens if there is two or more than two halogens in the same molecule? So that time the reaction of your SN2 reaction rate decreases. Why so? So see here, as the electronegative group is added to this system, that time and electrometric effect is also there. Okay, along with this your electronegativity, and also the steric strain increases because of the bigger size of your chlorine atoms. Okay, so the energy of the transition state does, this increases these factors. That means the steric strain and the larger size of the chlorine atom. Okay, the electrometric effect, this what it does, it actually increases the energy of the transition state and thus decreases the rate of the reaction. So I'll write it down so that you can copy it in your notebook. In cyclic system, what happens in cyclic system? In cyclic system, here cyclobutyl system. So cyclobutyl system, okay, cyclobutyl system are effective towards SN2 reaction. Okay, then your cyclopentyl system. Then if you go for your cyclohexyl system, they are relatively slow for SN2 reaction. Okay, in case of your cyclobutyl system means this kind of system. Okay, this is butyl, and cyclopentyl system means this kind of system, and cyclohexyl system means this kind of system. Okay, so if suppose there is halogen, okay, if suppose some tertiary group is there, okay, and this is the halogen is there, this is hydrogen. So what happens in cyclic system? Here the equatorial position is more stable than your diaxial position. These axial position, they get you can say they sterically, it is sterically hindered. So even if they go for your SN2 reaction very slow, they will go for your those products which will be in your equatorial position, which will be in your equatorial position. Okay, and then you can say axial position, they will have more sterically hindered, plus there is steric strain is there in your axial position. Mostly they exist in this form, where it is you have a system in your you can say they always exist in more stable form, that is your equatorial position. So in this case here, there is in equatorial position there will be change, or you can say addition of the nucleophile. But in case of axial position, SN2 is very very slow, it is not possible for SN2 reaction. Even if it will go through only your equatorial position. Here, the bridge-headed substrate does not go for your SN2 reaction. Here, this is the this is the one where the nucleophile is, or you can say the living group is. So here, this one will be this carbocation, whichever will form, is very very unstable. Okay, this hardly goes for SN1 also, so it will not go for SN2 also. So this is no reaction. Okay. This is no reaction for SN2, it will not go. Now we have discussed whatever structure, whatever kind of different kind of structural effect, okay, on the SN2 reaction rate. Second, we will see the effects of the solvent. Effects of solvent on rate. On rate. See here, the effect of the solvent on the rate of your SN2 reaction does not depend, it does not depend whether it is only your protic solvent or aprotic solvent. Protic solvent means those which has hydrogen and water, okay, and aprotic solvent means which does not, you can say, which is a solvent which does not have, ionic bonding. Okay, those one which has protic solvent, remember, protic solvent means here you have ionic bonding. Ionic bonding is there. Okay, aprotic solvent means aprotic solvent, here there is no polar bond. No polar bond, that means no ionic bonding. Okay, polar bond creates ionic bonding. Okay, like this protic solvent is your water. Okay, aprotic solvent is benzene. There are some other solvents also. Okay, so see here, depending on the nature of the incoming nucleophile and that of the living group, SN2 reaction may be classified into these four types. Okay, where the first one is your neutral species, where the nucleophile is neutral but the living groups comes out to be your anion. That time what happens, those solvent which will stabilize this anion will be good for your SN2 reaction. That will increase the rate of SN2 reaction. That means in the first case, if you see the first case, if here it is a polar solvent, that means polar solvent means what, it will make hydrogen bonding, that it will solvate this anion, it will solvate this anion, and hence the rate of SN2 reaction will increase in the case of number A if there is polar solvent. Whereas if you see number B, here the neutral molecule, so here the nucleophile, attacking nucleophile is a neutral species. Again, see here what happens here, in this step there is no formation of your carbocation. Here also there is a neutral species which is going out. So in this case the effect of polar solvent will not be much. That means if you increase the polarity of the solvent, here the SN2 reaction will not increase much. It will be okay. There will be no change in the rate of the reaction. Here in this case, if suppose again see here the neutral species, here the anion is the attacking group and the group which is coming out is a neutral species. Here also see there is neutral species is coming out, so there is no requirement for hydrogen bonding or stabilizing this anion cation. So polar solvent will not do any much good to it. Okay, non-polar solvents will, it will be, the rate will be same. In this case, say in the last case also, see here also there's an anion, it is replacing, but here again there is a formation of an anion is formed in the reaction medium. So if there is a polar solvent, then again the rate of this reaction will increase little bit, but then also it will increase little bit the rate, but for these two it will remain the same. So the effect of the solvent for these two, if it is aprotic solvent, then the reaction will be rate of reaction will increase for this if it is aprotic solvent. Okay, and here the reaction, these two, and the first and the last one, here the protic solvent will increase the rate of the reaction. So remember this is very much different from your SN1 reaction, and you should take note it down. I haven't seen any video which has been done in so much details about your SN2 reaction. So the last factor is the effect of the nucleophile on the rate. Since the single step SN2 reaction involves substrate and the nucleophile both, the rate of SN2 reaction depends largely on the concentration of the nucleophile and its nucleophilicity. So it depends on nucleophile file, okay, and that also in turn depends on this nucleophilicity. Nucleophilicity means the one which is very much prone to nucleophilic attack. That means which is a very good nucleophile will go for your very good SN2 reactions. So let's see what it is. Here what is said as it is directly proportional to the nucleophile or nucleophilicity. That means if the concentration of the nucleophile increases, then rate of SN1 will increase, and if the concentration of your nucleophile decreases, then the rate of SN2 reaction will also decrease. Okay, so I hope you understand. The if concentration is more, so SN2 reaction is more, concentration is less, SN2 reaction is less. And the last effect is the effect of the leaving group. Okay, the okay, so what will happen, the or you can say effect of the leaving group on the rate of the SN2 reaction. The rate of SN2 reaction is independent of the nature of the leaving group. So the group of lower basicity and high polarizability will increase the rate of the reaction. So it is independent. So you can say it is independent of nature of the leaving group. It can be any kind of living group. It does not matter. It does not care about it because the rate does not depend upon the living group. It depends on the substrate and nucleophile. And in SN1, it depended on the rate of your formation of carbocation. That means the faster the living group goes, the faster formation of carbocation. So there it depended. But here it is independent of the nature of the group. Okay. So groups of, you can write it down, groups of lower basicity means good nucleophile, and high polarizability. Basicity means the tendency to give the nucleophile, give the electrons and but go out of the reaction, not forming a bond. Whereas someone which is a good nucleophile, it will go and make the bond with itself, and it will share the share the electrons rather than just giving it. So groups of lower basicity and high polarizability increases the rate of your SN2 reaction. Okay, for halide ion, I minus is more than Br minus, more than Cl minus, and more than F minus. On the other hand, here, so this is a very good living group. So you can say, SN2 reaction will decrease in this order. Okay, so whether it is a good living group or not, it doesn't matter. On the other hand, on the basicity, the reactivity rate H2O, okay, is greater than ROH, and it is greater than HO minus. It means this one will go SN for your SN2 reaction more faster than this, than your this. So this one will go for more SN2 than this one, and then this one. Why so? Conjugate bases of the weak acids are very poor leaving groups since they are strong bases. See, if acid is a weak, that means its base, which will form after giving out H plus ion, will be very, very strong base, and hence they are very much poor leaving group since they are strong bases. So they will be not good for your SN1, SN2 reaction. Whereas Cn minus, okay, Cn minus cyanide. Cyanide is the uh, conjugate base of weak acid. Base of weak acid. HCN is a weak acid, HCN is a weak acid, so its conjugate base is a very much, it's a conjugate base of the weak acid, hence, and does not act. Example, this is the example of this one which I'm explaining, does not act as your living group. Okay, so these kind of group will not be living in nature. So hence, if this kind of group is there, so SN2 reaction rate will decrease, because if this is not going from the reaction medium, then how will the attack take place with the other nucleophile? So this was all today about your SN2 reactions. Okay, then we will go for questions based on your SN1 and SN2 reaction in the next upcoming video. And there I will explain which one will go for your SN1 or SN2 reaction, taking out all those examples which comes your NEET examination, your competitive examination and other things. Okay, so in this video I will make this, I'll say bye-bye. We will see in the next video. We'll solve the questions in the next video actually.